We have a special talk today by Damiano Caprioli. And I guess he doesn't need any introduction. I really planned one, so take it away.
Thank you, Ben. So it's really, I'm really happy and delighted to give you some overview of what I've been doing for the past 3 years or so with my group. Clearly, it's impossible to cover everything, so I asked for 3 hours, but it was harsh. No? So let me just start by introducing the group of people who work with me here in Chicago. So we have a postdoc. You have never seen Siddhartha probably because he's arriving tomorrow. So and then there are grad students. Thomas is a master's student, and undergrads. Some of them have graduated already. I won't go into the details. I'll show something that has been produced by most of them, not by everybody for obvious reasons. And some of these projects, some of these collaborations spent several papers, others are work in progress, but this is, I'm really happy to work with such a great ensemble of people. So today I'm going to tell you about some astrophysical objects that I find very interesting. So the remnants of supernova explosions, so SNRs, not signal-to-noise ratios, but supernova remnants. And I'm giving this in a sort of a picture of like 3 stages of life, and in particular of the non-thermal life of supernova remnants. So I would say that the early stages, the childhood of supernova remnants, where we see them a few days, months, years in some cases after the explosion. And since they are rare, we don't see those in our galaxy, but in other galaxies. These are typically seen in the radio, but also in the X-rays. And these are interesting because they probe, since the shock goes through very, very quickly, they probe the layers of material that have been ejected by the pre-supernova stages. And I'm not going into much details about these radio supernovae because we had a colloquium last week by Raffaele Margutti that actually covered this topic very well. The adulthood of the prime of the life of supernova remnants is when they, and these we have also galactic objects like Sophia, Tycho, Kepler, and so on. In these cases, we have basically galactic cosmic ray factories that we know and love. I'll tell you more about how particles get accelerated in these shocks in the following. And eventually, they die off. They merge with the interstellar medium when they become old. This is the jellyfish nebula, or IC443. But actually, here there is an H2 region, there is another supernova remnant, G1.189.6, and so on. And this is the stage where stars, where massive stars that exploded as supernovae, give back energy, momentum, mass, and also chemical enrichment to the galaxy. And this is important because it is the so-called stellar feedback that is important for understanding galaxy evolution, how star formation is self-regulated, how stars are born, and so on. So these are the 3 stages of life, and in a nutshell, the typical evolution of a supernova remnant looks like that. So there is an ejecta-dominated stage where the outer layer, let's say that we can consider that most of the mass is in a dense shell that expands at a given radius, it expands with a given velocity, and in the ejecta-dominated stage for the first 1,000 years or so, the radius, this is a ballistic expansion. The radius grows linearly with time because it doesn't feel the inertia of the swept-up material. When the swept-up material becomes comparable with the mass of the ejecta, this shock has to slow down, and instead of entangled independently, found that in this stage where energy is conserved, there is a self-similar solution such that the radius expands with the time to the 2/5. And this stage lasts for about like 10,000 years. Eventually, when the post-shock temperature drops below 1,000,000 Kelvin and so on, semi-forbidden transitions allow the post-shock gas to cool down, and effectively the shock becomes radiative, the remnant becomes radiative, starts losing energy, and this happens, so it slows down dramatically, and this happens around like -5 years, just to give you a flavor. So I'm going to go Benjamin Button in this kind of story of life of supernova remnants, in the sense I'm starting from the end and going back up to childhood at the end of the talk, because there are different techniques that are used in these different stages, and this helps the narrative. So the old age is when the stellar feedback happens. And in particular, one of the things that I'm interested in, since it's the non-thermal life that I'm interested in, is whether cosmic rays that are accelerated, these supernova remnant shocks, do anything in terms of controlling the evolution of the supernova remnant. And the idea here is that the general evolution of the remnant, we went through quickly the ejected illuminating and the set of Taylor stages, but if you go a bit more in depth in the radiative stage, you can write down a simple equation in this thin shell approximation. Yes?
So you're talking about supernova. Do you care if it's type 1, type 2, type 2b 27.3, or?
I don't care about phone numbers for this specific.
Just garden variety supernova.
Yeah. So this is basically the story of a release of 10 to the 51 Earths, give or take a factor of a few, into the interstellar medium. And this is actually the strong explosion limit, technically. The original book by Sedov has actually atomic marshal on the front page. So this kind of evolution happens in different contexts. So this is basically a bomb that explodes in interstellar medium for this stage. And if you write the one-dimensional conservation spherically symmetric equations for conservation of mass, momentum, and energy, you end up writing something in this thin shell approximation, where you have approximated the remnant as a hot bubble, so a bubble which is underdense and filled with hot plasma, with a dense shell around where all of the swept up mass is. And the equations simplify dramatically, and you end up with something like this, which is the mass, this is the momentum carried by the shell, the velocity times its mass. And this evolves according to the force, so the pressure per unit, so the force per unit area, which is the pressure, that depends on the difference in pressure between the hot bubble that is pushing and the interstellar medium that is opposed. So actually the radiative stage, there are two different stages. One is for the pressure driven snowfall, where the so energy is being liberated because the post-shock gas is cooling down, but the shell is still overpressurized, so it keeps expanding. And eventually, when you achieve a pressure equilibrium between inside and outside, this goes to zero and the momentum saturates. So this is the final momentum that a supernova explosion deposits into the galaxy. Why do we care about the momentum that it deposits? It's because all these remnants go through this radiative stage, so energy is actually radiated away very effectively. So the history of stellar feedback, as Andrei and collaborators showed, is mostly a history of momentum feedback rather than energy feedback. You just displace the circumstellar medium. And so this momentum is what makes the galaxy aware that a star has exploded, and on a time scale of 10 to the 10 to the 5 years, you can actually start pushing the wind, you start launching the wind, suppressing star formation, and so on. So what we did with Rebecca Dizing was to study how cosmic rays work in the evolution of supernova remnant, because even if cosmic rays are accelerated with, like, say, an efficiency of 10%, so if the shock channels 10% of its energy into supernova remnants, into cosmic rays, this energy cannot be radiated away because they don't cool down with line emission. So effectively, and they also have a slightly different adiabatic index, so these helps. So in this, using this thin shell approximation, we worked out the first semi-analytical solution that goes smoothly between the set-off and the radiative stage for finite acceleration efficiencies. This is compared with an adiabatic solution that extends forever. And you see that depending, so this is the evolution of radius and velocity, and you see that the final dot is when the velocity of the shock becomes equal to the thermal pressure, the sound speed of the interstellar medium. Basically, when the shock is not a shock anymore. It's the official death of the supernova remnant. And you see that this is pushed forward in time, and so its remnants grow larger until later times and eventually deposit more momentum. This is the momentum deposited normalized to the case without cosmic rays. The case without cosmic rays perfectly reproduces fully numerical simulations of supernova remnant evolutions. And you see that eventually you can end up depositing, just with a 10% efficiency in cosmic rays, you end up depositing a factor of 3 to 5 more momentum. And believe it or not, this is exactly the kind of a factor that galaxy simulators need to reconcile the standard feedback that would be given by this simulation without cosmic rays with the feedback that is needed to produce Milky Way-like galaxies. So this is a physical reason over how this boosted, sometimes it's put by hand, or a factor of a few to 10, actually can be implemented. And this is also another way of seeing this for different densities of the interstellar medium and different acceleration efficiency. You see that the larger the density, the circumstellar density, the more important radiative losses are, and so the more important is the contribution of cosmic rays. However, this saturates, and that's the difference between solid and dashed lines, when at some point cosmic rays start losing energy because of cosmic collisions, and so they produce gamma rays, which are very nice, but they effectively start losing energy. So this is the factor of 10 that you can achieve in density in stellar environment. And the story of how supernova remnants affect the overall galaxy actually goes beyond the simple momentum deposition, because these cosmic rays that are produced eventually escape the remnant, and they can carry the 10 to the 50 Earths, so the 10% of the energy of the supernova itself, to large distances. So you can, in principle, deposit energy and momentum also in the halo or in dense regions. And this has been shown now there is basically consensus between several groups that cosmic rays can have an important role in regulating galactic dynamics. The tricky part, though, is that this depends very strongly on how cosmic rays are transported in the galaxy. If you assume that they diffuse with the standard diffusion coefficient that is inferred for our galaxy, you find some kind of results. If you change this diffusion coefficient by a factor of a few, or if you allow the relative drift between the cosmic rays and the gas, which actually leads to basically cosmic rays to slip through and end up depositing energy at larger distances, you obtain completely different galaxies. These are simulations by Vygotsky and collaborators. This is the case where the cosmic rays have a drift with the gas, so they start basically pushing like a piston, and you get this kind of galaxies. These are density, energy density in cosmic rays and magnetic field structure. But if you allow them to slide with respect to the gas, and you change the diffusion properties just a tiny bit, here we're talking about tens of kilometers per second, so this is 4 times the FN speed. Yes?
I missed, how do they, when and how do they leave those supernova remnants that you're telling us at the beginning?
Well, at some point, so when they go to the, when remnants die off, their magnetic field also dies and gets diluted, at least, eventually dissipated through some kind of damping. And at that point, the diffusion length of the cosmic rays becomes comparable with the size of the remnants, so they start leaking out.
So that does not interfere with what you were telling us earlier about the cosmic rays being available for the...
No, they are strongly confined until the remnant is supersonic, and then after it has that's been diluted into the galaxy, they start leaking out, but you still have an overdensity of cosmic rays close to the sources, so large-scale gradients that can drive currents and fluxes of cosmic rays out of the hill, for instance. And you see that you get completely different galaxies depending on these microphysical parameters. Yes?
So I don't understand that last line where you say a small difference in the drift between cosmic rays and gas makes a big difference. Wouldn't the magnetic field make the big difference? And if you have an ordered magnetic field, wouldn't that dominate what the cosmic rays are doing?
Absolutely. So the picture here is that there is a larger scale magnetic field with some perturbations on top. So the cosmic rays would stream along the magnetic field, but this basically makes a current. So the cosmic rays themselves are generating a current that generates some transverse magnetic field. And this transverse magnetic field that is self-generated by the cosmic rays is responsible for their own scattering. So they, on top of this large scale streaming, they diffuse back and forth and sideways. And at the exact level of the relative, so the drift along the cosmic rays versus the diffusion velocity along the magnetic field versus the diffusive velocity depends on the strength of the self-generated turbulence, and that makes a huge difference. That's why I'm advocating for the need to simulate cosmic ray transport self-consistent, in the sense that you need to take into account the non-linear coupling between these cosmic rays that on one hand are trying to escape, on the other hand they are generating some fields that is self-confining them. The exact level at which this balance between escape and self-trapping happens is the key to understand what goes on in realistic environments, also in our galaxy. So, yes?
So I'm not clear what you mean when you say diffusion coefficients span more than 5 orders of magnitude. Do you mean measured diffusion coefficients, or do you mean theoretically predicted ones, and do you mean with space or energy?
That's a good question. So at a given energy, if you wanted to accelerate particles up to the need, up to the 10 to the 6 GeV in supernova remnants, you need a diffusion coefficient that is 5 orders of magnitude less than the one that is inferred in the galaxy. So when you move from the supernova remnant environment, where you need a fast diffusion rate to accelerate particles, to the galaxy, when these particles are effectively almost free streaming, there are 5 orders of magnitude, 5, 6 orders of magnitude at a given energy. If you go smoothly between one and the other, or if there is an area, a sphere of influence of each source where you go with continuity, it's something that is not known. So what people do is they simply plug the galactic diffusion coefficient when they prescribe that cosmic rays are escaping, and that effectively is imposing a jump of 6 orders of magnitude in the diffusion coefficient just there.
Thank you.
So, and what we are doing with Colby, Haggerty, and then Enswaldo is to do kinetic simulations to model this transport self-consistent. I won't go into details about this specific part, but this is something that is badly needed to properly address the role of cosmic rays in galaxy formation. So, going to the adulthood stage of supernova remnants, it's the moment to see how do we get these cosmic rays in the first place. And I like to start, to bring to your attention this quote by Philip Morrison that says that in 1954, Einstein remarked that there were two easily observable phenomena that show the deep fundamental lack in our knowledge of the physical world, namely the cosmic rays and the terrestrial magnetic field. I would say that we are 65 years later, and still these are outstanding questions. And some ask also about the terrestrial magnetic field in particular. So the idea of how cosmic rays are accelerated dates back to Enrico Fermi, who 70 years ago in this, not in this building, but nearby, put forward the idea that is very simple in its simplicity, in the sense that, in its generality, in the sense that if you have an elastic collision against the wall, the particle comes back with the same energy. But if the wall is coming towards you, the particle comes back with more energy. If the wall is receding, the particle comes back with less energy. Now, if you imagine a particle that is traveling in a sea of walls that are moving isotropically, you still have more head-on collision than tail-on collision because you have basically velocity aberration. The same reason why you get more weight in the front and in the back when you bike. Head-on collisions are more probable than overtaking collisions. And so on average, particles that are scattered back and forth gain energy. And then in the late 70s, people realized that there is a physical condition, namely around the shock, where all the interactions are actually head-on collision. Namely, this is called the diffusive shock acceleration, in the sense that if you have a particle that diffuses back and forth across a shock, so upstream is the unperturbed, is the pre-shock medium, downstream is the post-shock one. If you are upstream and you go downstream, you see the fluid coming towards you, so it's effectively a head-on collision. Then once you are downstream, you get isotropized, and if you happen to recross the shock, you still see the upstream flow coming towards you. So every time you jump back and forth is as if you were squeezed between two converging flows. So this is not just effective, but it's also incredibly general because this mechanism naturally produces power law distribution in momentum. And this power law, so the number of particles with momentum p is 4 pi p squared, p to the minus alpha. This slope is quite important, it will become important in the following as well. This slope only depends on the compression ratio, so on the amount of compression that you have between upstream and downstream, which is also the same amount of in the shock frame of how much the fluid velocity changes. The long story short is that this compression ratio actually saturates to 4 for large Mach numbers. So when the shock is strong, as long as the shock is larger than, it moves faster than a few tenths of kilometers per second, which is typically the case. Here we go up to 10 to the 4 kilometers per second. The Mach number is very large, the compression ratio is expected to 10 to 4, and this law also converges to 4. So strong shocks should produce p to minus 4 distribution in momentum. This is true whether particles are relativistic or non-relativistic. If you wanted to know the spectrum in energy, you have to convert energy, momentum into energy. This actually is different if you are relativistic or non-relativistic. But for relativistic particles, these will become the e to minus 2 spectrum that is typically, the energy spectrum that has the same energy per decade, which is usually associated to diffusive shock acceleration. But the important thing is that this is a very strong theoretical prediction that under basically any circumstances you should see the supernova remnants e to minus 2 spectrum for relativistic particles. It doesn't depend on the details of how particles scatter. And the other thing is that supernova remnants typically show some X-ray bright rings that are very thin, like a quarter of a fraction of a parsec. And in order for TeV electrons to lose energy in a fraction of a parsec, you need magnetic fields that are as large as hundreds of microgauss, which is a factor of 100 larger than typical magnetic field in the galaxy. So the nice thing is that supernova remnants are associated with incredibly strong magnetic fields. And large magnetic fields facilitate the transport of particles back and forth across the shock, so in a given amount of time allows you to achieve larger and larger energies. And the nice thing is that this magnetic field is actually a byproduct of the acceleration itself. So it's a self-consistent nonlinear process where particles are accelerated, they generate more magnetic fields, so they are accelerated even faster and to larger energy. It's a runaway process in principle. When it stops, that's a good question, and that's the reason why actually it's not obvious that when acceleration is efficient up to which energy, and also what is the origin of the chemical composition that we see in cosmic rays. We know that not only protons are accelerated, and I'll talk more about this in a second, and are there any observational counterparts of these? Well, in order to address these problems where we need a self-consistent coupling between accelerated particles, thermal gas, and magnetic fields, we can use a so-called particle in cell approach where you have a grid, you define the electric and magnetic field, you put electrons and protons on top, evolve them according to the Lorentz force, use the currents to advance Maxwell equation, and keep iterating until you have time on your supercomputer, because this is very expensive. A possibility of mitigating this effort is to consider electrons as a fluid, and so only retain the kinetic nature of the protons. And this way, you don't have to simulate the small length and time scales that are associated with the electrons, and you can simulate more macroscopic scales and still have a coherent and self-consistent description of accelerated protons and the magnetic fields that are generated by the protons themselves. So this hybrid approach is what I will use in a second. But in general, you can say that one can say that in order to study the microphysics and the astrophysical scales of supernova remnants, you need a multi-scale approach where you need peak simulation that model electrons and ion ab initio, or if you can go to mesoscales using hybrid codes that simplify the electron physics, or even you can have like an MHD background with the kinetic particles on top. It's sometimes called a super hybrid that allows you not to waste time in evolving the thermal particles that you should more or less know what they are doing. But eventually, all of these kinetic processes need to be compared with observations, and so you need something that is more agile and computationally cheap, and that's why we developed this semi-analytical approach. It's called CRAFT, so Cosmic Ray Analytical Fast Tool, that I'll mention in a few minutes. So let's focus on these like mesoscales. So for the moment, so hybrid simulations where ions are kinetic particles. So this is a typical simulation of collision of a shock. You send a supersonic flow against the wall, and the interaction between the ingoing and the reflected flows produces a shock that moves to the right. In the top panel, I show the density plus the trajectory of individual particles. In the bottom panel, the magnetic field, which this will be the out-of-plane component, which in the beginning is zero. This is basically just grid noise, because the field is oriented along the shock. So this is how the simulation looks like. You see the compression, the density. This is a compression ratio of 4, as we know from standard fluid theory. And particles start, they gyrate around the magnetic field. They start scattering back and forth across the shock. Every time they interact with the shock, they gain energy, so their tail becomes longer. The code also changes. And you see that these particles start generating some magnetic field perturbations ahead of the shock that allow them to scatter back. So in diffusive shock acceleration, you don't need to have a large magnetic field to start with, because you naturally generate currents that generate these fields for you. And as a result, the distribution develops a non-thermal tail that accommodates for about 10 to 15% of the energy of the shock. So you generate, you still have a Maxwellian distribution, that has a slightly smaller temperature because you have to conserve energy overall, and you generate a non-thermal tail with a maximum energy that increases with time because you have more and more interactions with the shock. So this is the standard picture that arises from kinetic simulation. Let's see a bit more the large-scale structure of this. So this is density, total magnetic field, parallel and out-of-plane components of the magnetic field. And you see that these current in backstreaming particles actually drills holes in the upstream, excavates cavities, amplifies the magnetic field by large factors, makes the shock surface turbulent, and then there is additional sort of turbulent dynamo acceleration, amplification of the magnetic field in the downstream, and overall you end up with a magnetic field that is orders of magnitude larger than the initial one. The actual way in which this field grows was postulated already in the late 60s and 70s by Karlsruhe, Stirling, and so on. And this goes under the name of streaming instability, so it's the plasma instability driven by the cosmic rays themselves. The usual problem of this instability, though, is that it tends to quench itself when it becomes nonlinear. So when delta B over B becomes of order 1, since this is a resonant instability that is generating waves that are in cyclotron resonance with the cosmic rays themselves, when delta B over B becomes of order 1, this resonance turns on and scatters and disperses the current. So then you cannot go beyond the delta B over B of order 1 with this instability. And then in 2004, Bell pointed out that actually there is another mode that is non-resonant in the sense that it is right-handed and it is much shorter wavelength with respect to the Larmor radius of the cosmic rays, that actually grows faster than the resonant mode of the classical streaming instability, and can go non-linear very easily. So you end up not disrupting the current. And this was a breakthrough because in order to accelerate particles up to energies as large as they need, you need amplification factors of order of tens or 100. And the band instability seems to be able to produce this. The problem is that there are no self-consistent calculations. There were self-consistent calculations of the saturation of this instability. So what is the actual maximum magnetic field amplification that you can carry out from a given cosmic ray current? This is what we are doing with Georgios and Colby. This is proceedings, but we have a paper that's going to be ready soon. This is a typical simulation. We have a periodic boundary condition, initial magnetic field, a current in cosmic rays that flows this way, and you see that you start developing magnetic fluctuations, and if you keep pushing this cosmic ray current, actually when the cosmic rays couple with the flow, they start pushing and displacing the plasma itself. And this actually is the mechanism, is the reason why the instability saturates, and the magnetic field that you get out is basically sort of equipartition with respect to the energy that you put, the free energy in the cosmic rays you started with. This kind of magnetic field amplification and this saturation at very large levels is what you need in order for particle acceleration to work and for supernova remnants to accelerate particles up to the supernova remnants.
Can you just
Yes.
say one more time for the slow to catch what the saturation mechanism is? I mean, the equipartition, I mean, at each stage you told us that the energy increases, so you could achieve equipartition, but then the energy changes, so
the energy.
So what exactly determines the saturation? I didn't get that.
There are actually two different conditions that happen to be realized at the same time. One is that when the cosmic ray drift velocity with respect to the background becomes a order of the Alfvén speed, the instability quenches itself. So if you initially the cosmic rays were drifting, but then they couple with the plasma, so the plasma is set in motion, the relative velocity drops. While this happens, also the small wavelength mode that was triggered by the bell instability has also grown to large scales. So at that point, it also became resonant with the cosmic rays themselves. And you can show that these two conditions happen at the same time. So it's really sort of a resonant coupling between the fastest growing mode and the reduction of the relative drift, which basically kills the cosmic recurrent in the plasma flame. And that gives you the saturation that it can also be seen, as Bell originally suggested, as the tension in the amplified magnetic field that balances the J cross B force in the cosmic rays. Okay, and the nice thing is that this magnetic field amplification is also inferred from X-ray observations, where you have synchrotron emission that varies on a few years time scale, in which you can put a limit of a lower limit of magnetic fields that have the order of a milligauss in these knots. And about the scale at which these fields amplify, you see typically structures that are like stripes, where the typical spacing between stripes is given by it actually corresponds to the Larmor radius of the particles that are generating the instability. And this is something that comes out from the microphysics as well. In the original paper by Fermi, the final note of his abstract was the chief difficulty of this acceleration process is that it fails to explain in a straightforward way the heavy nuclei observed in the primary radiation. The original idea of Fermi was not to use diffusive shock acceleration, but was turbulent acceleration in the galaxy, where it's a much slower process, and if cosmic rays are confined for billions of years, they would be disintegrated or they will undergo spallation. So that's why you cannot have heavy nuclei for such a long time. But if you have a faster acceleration process, then you may. And there is a sort of an urban legend about cosmic rays that you read in textbooks, that the composition of galactic cosmic rays is similar to the composition in the solar, the solar metallicity. This is true at the GeV energies, where, however, heavy nuclei are depleted by spallation. If you go look at the higher energies, like in the TeV range, where spallation is not important, you see that, okay, the pattern in the abundances in black dots, so solar system abundances and cosmic ray flux, is still similar, that you have stable and unstable elements. It's not that you have an excess of boron that is produced by spallation of carbon, and sub-iron elements that are produced by destruction of iron. But the point is that if you look at the, for instance, the iron to hydrogen ratio in solar abundances, this is more than 10 to the 4. In cosmic rays, is less than a factor of 10. So I wouldn't call these the same chemical composition, the same elemental composition. Because you can do this also for like carbon, nitrogen, and oxygen, and you come to the conclusion that heavy nuclei, so nuclei heavier than hydrogen, must be injected more efficiently than protons in order to explain the chemical abundances that we measure. So what we did was to run hybrid simulations with different species, also deuterium, because we can play God and put whatever species we want, helium, and what you see is that I spare you the details of how they start being injected and how the phase space evolves. The takeaway message is that if you plot the spectra of different species that have different mass and charge, you see that the downstream temperature scales with the atomic mass, which is to be expected because you have more kinetic energy to be thermalized. The maximum energy scales with the charge, and that's also expected because particles with the same Larmor radius should undergo the same acceleration, but if they have the same Larmor radius, particles that have a different charge have so a larger charge have a larger energy. What is absolutely non-trivial is that the normalization is of this non-thermal tail scales like A over Z squared. So we see a self-consistent over-injection of heavy elements, so like singly ionized helium or carbon or iron with respect to protons. And it's pretty large, so like for iron, this would be like 26 times square. And this is exactly what you need to reproduce the enhancement in heavy elements in galactic cosmic rays. We weren't expecting to be able to reproduce this scaling, but it came out naturally without any free parameter. This just has to do with how particles of different mass to charge ratio are thermalized and injected into the acceleration process, which requires a completely different order, which I'm not going through. Another interesting consequence of this is that if you take the typical cosmological abundance of helium, let's say 10%, this is a work that we are doing with Corey, Copper, and Marwa Bussi, we see that helium is boosted by a factor of A over Z squared, so it means a factor of 16 if helium is singly ionized. And so, namely, we would expect the helium to be as important as hydrogen, and in fact it is. So the shock ends up putting 15% of its energy into accelerating the helium. And so making the total efficiency of the cosmic ray acceleration closer to 30% than 10%. And since helium is not a test particle, it can also drive a magnetic field amplification itself, so you end up with a larger magnetic field. It helps you achieve a larger maximum energy, and also to produce more gamma rays due to nuclear collisions between protons or hadrons in general, and interstellar medium. So this is an interesting consequence that most of the emission, most of the gamma rays that we may see from supernova remnants don't come from protons, but come from helium. And this would be
Damiano, if you increase this traditional 10% efficiency to 30%, would it have huge implications for all previous estimates about supernovae, what they do in the galaxy?
A factor of 2, right? So yeah, so it depends. You can call it a huge implication, but yeah, it's a factor of 2 more energy. But I don't think that. Yeah. So yeah, with respect to 15, let's say the efficiency doubles for these for each accelerator. So since the supernova rate is uncertain within a factor of 2, I don't want to say that large scale simulations don't have this room to adjust these factors. This factor of 2, but on the specific object, it does make it quite obvious. Yes.
But presumably the gamma ray emission would be a limit on this, right? Like if it's too efficient, I mean we measure how
Absolutely.
yeah.
And it is. I mean, in the sense
Okay.
that we see that this is
consistent.
This is consistent.
Okay.
Typically, the efficiency that is required is a factor is about 10%. But again, you need to know the amount of gamma rays that you get also depends on the density of the medium, which is typically uncertain in a factor of 2. So saying if it is 10% or 20%, it's hard. But definitely, it's not 1%. Okay. So very quickly, instead, what can we learn about the childhood when supernova remnants are basically toddlers, in the sense that they are transitioning between supernovae and supernova remnants. These are particularly interesting objects because their evolution can be followed in real time with interferometry in the radio. And so you can see these evolving on a time scale of a few years. And this is great because you can basically have a sort of a tomography of the density of the medium around the supernova that basically shines light on the latest stages, the latest events of mass loss eruptions that the supernova, the star, underwent before exploding. And this is synchrotron emission. Synchrotron emission typically scales with the amount of energy that you have in relativistic electrons, the amount of energy that you have in magnetic fields, and then the density and the shock velocity as a normalization. So that a very popular way of phrasing this is that let's introduce this epsilon B and epsilon E which are the fractions of the bulk energy density, which is rho Bishop square, that end up in the magnetic field and relativistic electrons. Unfortunately, these epsilons are really poorly constrained theoretically, because in order to understand electron acceleration self-consistently, you need full peak simulations, which are terribly expensive for relativistic shocks. So that's why I'm going to briefly talk about these peak simulations. This is a map of shocks in different environments. You go from supernova remnants to heliospheric shocks and galaxy clusters all the way up to AGN and GRBs. And in observations and peak simulations are quite consistent in the relativistic regime, but we know that epsilon E and epsilon B have to be of order of 0.1. But peak simulations in the epsilon B you can get it also from hybrid simulation. That's why I put it as E2-2. But we really don't know what the self-consistently, what the amount of energy that goes into relativistic electrons is for relativistic shocks. And all in between is uncharted territory. And these radio supernovae are actually spanning this range of energy, this range of velocities, because they can be transrelativistic. So very recently, we performed the first campaign of transrelativistic shocks with the full peak simulations, where we found acceleration of electrons, and we were able to quantify that the acceleration of protons more or less stays constant at 10%, as usual, but this is where the transition between the 10 to minus 4 that you see, that we infer from observation supernova remnants for epsilon E goes to the closer to the 0.1 that is inferred from the relativistic shocks. So this was the first time that this regime was probed. And very quickly, if we wanted to go to large scales and do, especially when we are going to have incredibly large sets, incredibly a wealth of data that comes from follow-up of transients with the next generation facilities as LSST, for instance. You really need a fast way of modeling this synchrotron emission on single objects in order to infer the properties of single transient, single supernovae, kilonovae, and so on. So that's why we are developing this quick approach that instead of solving equations numerically with particle cell simulations, it solves what is called actually the Parker equation that for the cosmic ray distribution function, which includes advection, diffusion, the energy gain, some prescription for injection. I won't go into the details, but it's basically, you can find a self-consistent implicit solution of this equation, and you can close a loop, including also equation for conservation of mass momentum and energy for the cosmic rays, the magnetic field, and the thermal gas. And all of these runs in a few seconds on a laptop. So this is a kind of approach that can be used as a subgrid modeling in hydro or MHD simulations, or it can be implemented analytically with an analytical evolution of the remnant in order to model the time evolution that I showed before. Couple of examples of this application. This is something that we did for Tycho supernova remnant, which is a well-known object. It's a remnant of a type 1a supernova, and we were able for the first time to show that the gamma ray emission has to come from the decay of neutral pions produced in nuclear interactions. So this has to be a hadron accelerator. So this was the first time that we were able to associate gamma ray emission with acceleration of cosmic ray protons, also reproducing the radio and X-ray profile and so on. I'll skip this very quickly. Sorry, Rebecca, but time tempus fugit, as Martin used to say, because I wanted to talk about what is I think one of the most exciting problems an open question in these meetings. Namely, do we really understand the diffusive shock acceleration? So I told you that we have this beautiful theory that tells you that spectra for strong shock should be E2 minus 2 in energy. And then I showed you simulations, and then I showed you observation, but not really. And then let's look at what happens when our acceleration is of cosmic rays is taken into account. So at the non-negligible levels. So the slope in energy should be E2 minus 2 for strong shocks, and that also only depends on the compression ratio, which only depends on the adiabatic index. So this is the typical velocity profile, and this produces locally spectrum with this E2 minus 2. Now, if you have an efficient cosmic ray acceleration, then you can imagine that you have a bubble of a cloud of cosmic rays sitting around the shock. So this is an extra pressure that has to slow down the incoming flow. If you sit on the shock, the incoming flow has to slow down. This is a so-called precursor. And you can show very easily that if this happens, now you don't have a single compression ratio anymore. You rather have a weaker subshock that has a compression ratio less than 4, and a total compression ratio which is larger than 4. The problem is that now if you have a particle, a low energy particle, that diffuses closer to the shock, you will see a compression ratio that is smaller than 4. And instead, if you see a high energy particle that throws the total compression ratio, their spectra should, so the spectrum is not power law anymore, but it must become concave. And in particular, above 1 GeV, it has to become flatter than E2 minus 2. So the standard prediction in the presence of efficient cosmic ray acceleration is that spectra become harder or flatter than E2 minus 2. Now let's see what observations say. When you look at gamma ray observations from supernova remnants, and you plot the spectral slope as a function of age, for instance, you see that this is the test particle prediction, E2 minus 2. This is the nonlinear, this is the space that where nonlinear theory would put you. Instead, all of the remnants lie in a regime where their spectra is actually softer than the standard prediction. And on one hand, this is nice because it's impossible to do this with leptonic processes, so this is per se a signature of a cosmic ray acceleration, of proton acceleration, but definitely there is something that we don't understand in this theory, because it goes in the opposite direction. So this is one of those cases where the nonlinear corrections drive you away from reality instead of putting closer. And then let's go to even faster shock, the one in radio supernovae, the toddler remnants. And again, all of the slopes are inferred from radio observation that basically gives you the slope of this electron distribution. They are actually like typically E2 minus 3. So completely wrong. Clearly we have a tension between theory and observation, between type 1a supernovae, oh sorry, wrong satellite, or wrong scientist at least, and not Planck but Fermi acceleration, in the sense that the theory and the observations go in opposite directions. There have been a few ideas of how to overcome this issue. I'm not going into the details, except for this one, where people suggested that maybe this magnetic field amplification that wasn't there in the original theory is important, because eventually cosmic rays don't feed the compression ratio felt by the fluid, but feed the compression ratio felt by the walls they scatter against, which can be magnetic perturbation that have a finite velocity with respect to the flow. So maybe if the magnetic field is large, this velocity is not negligible, and these may change something. None of these ideas has been tested from first principle, so they are all speculations, basically. And there is enough freedom to change and adjust whatever theory you want. So for the first time with the simulation that we have run with Colby, where we have this new version of the code that also allows particles to become relativistic, we have seen we were able to run the simulation for much longer, And we saw the evidence of a cosmic ray precursor, in the sense that we see that the shock, the upstream flow slows down and heats up. And this is consistent with the fact that there is 10% of the energy in the cosmic rays that is going forward. And we also saw that there is a total compression ratio that gets beyond 4. So it's true that the spectrum becomes, so the compression ratio goes beyond 4, goes up to 7. And this is actually consistent with what is inferred by measuring the relative position between the forward shock and the contour discontinuity in tycho. The issue, again, is that if the compression ratio is 7, the spectrum in momentum is expected to be p to the minus 3.5 instead of p to the minus 4. So it goes in the direction of making the spectrum flat. So how is that possible? And fortunately, if we plot the spectrum as a function of time and compare it with the standard prediction, it fails miserably. And it actually goes the other way around. So the spectrum becomes softer with time. And it goes in the right direction to explain observations. Now the question is, why? And the nice thing is that in our simulations, we have all the physics where we can go and check what is the effect that is responsible for the coupling, the compression ratio fed by the gas, which is actually 7, as expected and as observed, and the effective compression ratio fed by the particles, which is much smaller. And so it turns out that the velocity of the scattering centers, so the velocity of the waves, is important. I spare you the details of the numerical details, but you can measure the velocity. You can do a Fourier analysis and see how both velocity, the magnetic fields are moving. You can do, you can take the moments of the cosmic ray distribution and see what is the drift velocity with respect to the drift velocity of the gas. But believe me, if I tell you that is as if the cosmic rays are effectively feeding a compression ratio that is smaller than the fluid. This way we reconcile both the fluid theory and the observations that require spectra that are steeper than the test particle prediction. And the larger the acceleration efficiency, actually, the steeper the spectrum. So this is really what closes the circle. I'm done with time, so I just flash here all the other projects that we are doing, and the new facilities that will enable new kind of multi-wavelength observations and follow-up of transients. I'm also interested in modeling heliospheric shocks, where you can actually compare the phase space distribution account of simulations with actual data, especially from NMS and the Parker Solar Probe. And I didn't have time to touch on acceleration of ultra high energy cosmic rays, which is something that was interesting. So I leave you with the task to decide to decipher the hidden messages that you always find in simulations.
I'm curious to what extent your hybrid pick calculations can be validated by doing laboratory experiments, like at LAPD, for example, or at Rochester.
That's a very interesting question. So definitely one needs to be in one of those facilities where plasma are actually collision-less, like so Rochester and Leaf, you can make it. And as far as I know, the technology is not there yet to make full collision-less shocks and test particle acceleration. But definitely there are campaigns, for instance, for studying the belt instability that I mentioned before. And that is actually an instability that starts as an MHD instability and then evolves into a kinetic one.
Right.
So you need a hybrid peak code to see at what level it saturates. You can't do that with an MHD code. So there is definitely a lot of room for
One of the interesting things that has been observed is a wavelength stability
Yeah,
in one of the shots. and
absolutely, yeah.
That would be ideal to
Oh,
explore
yeah,
what you
yeah.
like.
Yeah, yeah. Actually, the experiments with the wavelength instability, they have been supported by kinetic, by full peak simulations,
Right.
and yeah. I was thinking more about the hybrid ones.
The hybrid,
When you,
right.
when you involve proton physics, everything becomes a bit more. You need more energy, and the time scales are longer, which is harder to put the right diagnostics in place. Christine?
So I was curious about this, the magnetic fields that are amplified within the remnants and what happens to that field. So, I mean, the remnant expands, and does it contribute at all to the galactic magnetic field?
That's an excellent question, and this is something that when I ask to different people, where does the galactic magnetic field
Yeah.
come from? There are people who are absolutely sure that it comes from a turbulent dynamo that you can put there from the very beginning of the universe, and then it will naturally evolve to the steering of disks. There are people who say, oh, it's obvious that it comes from supernovae that are injected. I think that the fact that effectively the equivalent of 10 to the 49 ergs of energy end up in magnetic fields due to these cosmic ray-driven instabilities is something that has to be reckoned with. And since these instabilities are kinetic, I don't think that people who do large-scale simulations can actually inject these magnetic fields and compare the relative importance with respect to the seeds that they are born with some prescriptions. So my gut feeling is that these are important because this is a lot of energy. And also would naturally explain why in our galaxy, for instance, in interstellar medium, there is almost a good partition between thermal gas, cosmic rays, and magnetic fields. If the magnetic field were grown in a way that is independent of the cosmic rays, it's not obvious that the cosmic rays would be partitioned with that as well. Maybe a posteriori, but it's an excellent question.
So is the feedback to the galaxy as a whole, or do you ever have cases where it disrupts the cloud itself that was forming stars?
Simulations show that these may be, this feedback may be also quite localized if you have a star forming region. Actually, there is a positive feedback on the feedback in the sense that you can, the superposition of two supernovae is non-linear. For instance, for the cosmic rays, you can reaccelerate the population of cosmic rays that was produced relatively recently. And so it's possible that you have localized explosion, like fountains or localized winds that actually tended to suppress star formation in the regions where it would like to suppress star formation. So from this point of view, if it is local or global, it doesn't make much difference. The important thing is that you tend to suppress star formation where it happens the most.
A couple of quick questions. One is on the semi-analytic approach, which I didn't understand. I mean, the questions solved there very interesting, but the question is, at the end of the day, do you still have to feed in some phenomenological parameters that are based on something else?
So,
and the other question is the implications of what you do to larger scales, like in clusters. I mean, it's like the work that Irina is doing here. Is there any immediate connection to that?
Let me start from the second one, which is slightly more immediate. So the physics of cosmic ray transport in clusters is pretty similar to the physics in the galaxy. So once we understand how the different streaming stability work, changing the plasma beta, so making the plasma hot, a little bit hotter, as in galaxy cluster, it's relatively easy. In terms of shocks that you see in galaxy clusters, like in radio relics and so on, these are great laboratories, but again, their physics is not very different from the one that we are simulating for radio. Again, we need information about the electrons that are accelerated in these environments, match them with the radio observations, because that is what is needed. So it's definitely, galaxy clusters are great laboratories. But the nice thing of this approach is that this is really looking at the basic physics that can be applied to a large variety of astrophysical and space physics also environment. So the transport equation, very quickly, basically, this is actually accurate at the second order in U over C, where U is the flow velocity. So for non-relativistic shocks, keeping the first moments as just a diffusive term, so modeling them with a diffusion coefficient, that is a pretty good approximation. And so the question becomes, what is the magnetic field that goes into the field, into the diffusion, the spatial diffusion coefficient that controls how quickly particles go back and forth across the shock. And then there is the how particles are injected, which is something that has already been, we have solved this problem a few years ago, so I didn't talk about that today, but we have a pretty good idea of what kind of particles get injected and why, depending on the shock parameters. So these are the two microphysical ingredients that can be tuned based on self-consistent kinetic simulations, but it's not really a fine-tuning. We have a theory for how to write these things. So,
the reason I don't want to belabor it, you talked about the epsilon D, epsilon E, and
yes.
But here it seems like epsilon E, epsilon D would be different for each cell.
Epsilon B is actually well calibrated with hybrid simulations, because that depends on the protons.
No, but for this approach of the semi-analytic.
Yeah, in the so epsilon E is basically the spectrum of the electrons is eventually the spectrum of the protons modulo as factor that basically depends on epsilon B, and then it has losses on top. Losses are easy to calculate once you know the magnetic field. So you basically have one free parameter, if you want, even if you don't have epsilon E from first principles, you have only one free parameter, and you have, with this you have to fit a spectrum that extends over 20 orders of magnitude with the bands that goes from radio to X-rays, and for Supernova Remnants for GeV to TeV, gamma ray. So the system is way over-constrained, and having only one free parameter for which we don't have a theory is really not an issue. And the epsilon B, the magnetic field, actually enters in 3 different places, because it tells you the strength of the synchrotron emission, the maximum energy you can accelerate particles to, which is the end of the spectrum, let's say, and also how cooled the electron spectrum is. So basically the relative strength between the radio and X-rays also depends on the average magnetic field. So having a theory for epsilon B that fits simultaneously 3 different observables, which is what we showed, for instance, for typo, is really not an issue. So it is there. Yes?
There's one thing I don't understand, and many things, but how to fit in the big scale picture of the interstellar magnetic field in our local neighborhood of the galaxy with the kind of detailed, information you're presenting. Because we know from pulsars that there is an ordered magnetic field between regions thought to be spiral arms, and as soon as you go in between, away from the ordered magnetic field, you see a lot of super bubbles. So how do the cosmic rays in your acceleration models couple between this region, which is full of disturbed magnetic fields, with the ordered field in the inner arm region?
That's an excellent question. So observationally speaking, so in terms of cosmic ray transport, the observables are basically the secondary to primary relations, like the amount of boron over carbon, beryllium 10 over beryllium 9, and so on, stable to stable elements, isotopes, and so on. And at the zeroth order, all of these variables, all of these observables, including the anisotropy, can be fitted with assuming a diffusion coefficient that is homogeneous and isotropic, so it doesn't make any difference between propagation along the magnetic field or perpendicular to them. So from the point of view of observation, there is really no way to constrain the importance of all the structure that is there, that is there in the local magnetic field. From the point of view of simulations, actually you can play games. You can see what happens if you go from a region where if you have a strong guiding field with respect to a region that is like a star-forming region, a bubble. Another problem for propagation in the galaxy is actually the presence of neutral gas, because Alfvén waves are naturally damped by iononeutral damping in quasi-neutral plasmas. And that traditionally has been an issue. Understanding how cosmic rays propagate in dense environments is probably one of the most important issues. And actually, we started a project with Corey to add neutral hydrogen to the hybrid code and couple hydrogen and protons via ionization and charge exchange. And hopefully we will be soon able to tackle this kind of problems, including iononeutral damping, shocks propagating to partially ionized regions, whose dynamics is different at the zeroth order from the one that I just mentioned. And here there is a new set of diagnostics like Barnard line emissions that have their own peculiarities, golden line with that don't agree with the theory, with what you would expect, but they agree with the theory once you include some extra physics, like a neutral induced precursor ahead of the shock. I'm divergent, sorry.
Okay, I propose we dismiss people. So let's thank. Welcome to